Okay. Hello everyone. My name is Dylan, and today I'm going to talk about this incredible security research paper called Frankenstein Advanced Wireless Fuzzing to Exploit New Bluetooth Escalation Targets. And this was written by Jane Rugg and Jiska Klassen. And so, start off, if you were to have, let's say, like a smartphone in your pocket, or like a wireless headphones in your backpack, or even a smartwatch on your wrist, well, this research paper is going to directly affect you. And the researchers in this took basically Bluetooth chips inside these everyday devices I just named, and they figured out how to completely compromise them. Jump, basically a jump from the Bluetooth into the Wi-Fi chips, and they were even able to crash the host phones like entirely, which is crazy. And before I dive into this whole presentation, I want to show like a quick table of contents for what I'll be talking about for the next, what it is, hopefully like 20 minutes. So first, we're going to look at some historical background about the problem of the Bluetooth black box and why the testing is so difficult. And second, I'm going to talk about like the monster, which is like the actual Frankenstein emulation tool that the researchers use that they build to solve this problem. And then third, I'm going to talk about like we're gonna look more into like we call it like the break, like the actual zero-click exploits and the cross-chip attacks that they successfully put off. And then finally, I'm gonna wrap it up with the flaws and discussing the limitations of their tool and why patching these devices are like a complete nightmare. So to better understand this whole research paper, well, let's take a look back at the historical context and why this whole research is a big deal. So basically, Bluetooth is absolutely everywhere. There's around like 4.4 billion Bluetooth devices being shipped in 2020 alone. And despite how common that is, while wireless communication standards have been, you can say, like very troubled in the past with the history, with the security. And why is that? Well, that's because the firmware that runs on these chips is it's basically almost always closed source. And unlike the open source algorithms we usually like study, to these security researchers, the blue chip the Bluetooth chip, sorry, inside your iPhone and Samsung Galaxies is basically effectively a black box. So how were they able to basically find vulnerabilities in the black box? So basically, the security research used a technique called fuzzing to uncover the remote code execution or the RCE. And what fuzzing means is basically throw massive amounts of random mutated data at a system and watch to see what makes it crash. But there is like a huge like little problem with this. So basically, the traditional over-the-air fuzzing actually like sending corrupted Bluetooth packets through the air to a physical chip, it comes with like a lot of problems. It's very, very painfully slow, and it has limited repeatability, so you can't repeat it a lot, and it severely restricts your ability to like debug if something were to go like wrong. So like imagine you were trying to pair your like Bluetooth headphones to your device millions of times over the air just to test for bugs. That's how long like this would take. That's the problem with this that they had. And I want to go into more of this and why it's so difficult. It all comes down to the massive timing constraint. So inside the firmware, there's this Bluetooth core scheduler, or the BCS you can call it. And this scheduler is called by an interrupt exactly every 312.5 microseconds, which corresponds to exactly half a Bluetooth slot length. So if a traditional over-the-air buzzer causes even a tiny delay or even a minor crash, the chip will miss this 312.5 microsecond window and the connection just drops immediately. So that means you have to start all over, and the hardware's strict timing makes over-the-air fuzzing basically Basically, it's impossible. So now with all that, that brings us to the core concept of this whole research paper, which is the Frankenstein framework. The researchers realized that attacking the physical chip over the air was a dead end. It's not going to be an option for now. So instead, they built a fuzzing framework based on advanced firmware emulation. They extract the firmware dumps from physical chips and they bring them, you can say, back to life inside a computer emulator called the QEMU or the QEMU. And by doing this, they can provide fuzzed inputs to a purely virtual modem, cutting out the strict wireless transmission timings like completely out. So, how do you emulate the code you can't read? So basically, what this Frankenstein takes, what this Frankenstein does, it takes a literal snapshot of the memory from the physical device, and then they place a custom like hook within the physical chip's function. So when executed, this hook pauses, the device interrupts, and disables its safety's watchdogs, and slowly copies out the entire memory state via the host interface. So it's basically what it does. It's basically taking a picture of the chip's brain right in the middle of a dot. It's crazy. So once they had that raw snapshot, they had another problem because the snapshot, it's just raw binary data without any symbols. So what they did was the Frankenstein reassembles this raw dump into an executable and linking format, or you can call it an ELF file. And this was a massive breakthrough for them because it allows them to compile their own C code and leak it directly against the captured firmware image, which was big for them. So now that the firmware is inside the Linux emulator, they've come into another roadblock problem. So now that the Frankenstein runs in Linux user mode, which doesn't support the hardware interrupts needed by the firmware, in order to bridge this gap, the Frankenstein has to rely on custom C hooks. The researchers modified the firmware to intercept function calls and simulate things like hardware timers and thread context switches. And because these hooks were written in C and embedded right into the firmware, they run super, super fast, like outperforming existing hooking engines like the Unicorn. And they run so fast, it's faster by like 12.5x faster, which is big. So because they are in an emulator, they can be much smarter on how they fuzz. So instead of handling all the input data as a single random binary large object, they used what is called coverage guiding fuzzing. So this relies heavily on probability. The fuzzer maintains a population of sequences and selectively mutates individual packets to reorder and it reorders them to see if it triggers new code paths. So by doing this, they successfully reach 9.4% total code coverage of the firmware. So if you only reach 9% of the code and find three zero-click vulnerabilities, how many bugs do you think are hiding in the other 91%? So there you go. So why does the speed and coverage matter? So because of the full stack approach, the Frankenstein emulates the firmware fast enough that it can actually maintain interoperability with the attached operating system. They hooked this virtual they so what they did was they hooked this virtual Bluetooth chip up to a real Linux BlueZ Bluetooth stack. And because it's so fast, the Linux driver doesn't time out. So this allows the researchers to trigger and observe realistic full stack behavior. So we can go into how exactly they exploited this setup. So what they did was the Bluetooth firmware is based on ThreadX, a real-time operating system which is optimized for embedded devices. The ThreadX handles dynamic memory using pools called like the block buffers, where free chunks are managed using a singly linked list. And the researchers found a way to easily overflow this heap by sending a payload that is too large, and the attacker overwrites the pointer of the next free block in the linked list. And by controlling the pointer, the attacker creates a write what where gadget, allowing them to write malicious code anywhere in the memory to achieve this remote code execution, RCS. It's kind of cool. So, using this method, they fuzzed the parts of the firmware that can be reached prior to pairing, and this is critical because it allows for zero-click attacks. The victim doesn't have to accept a prompt to get hacked. So they discovered the three zero-click RCE vulnerabilities in Broadcom and Cypress chips. And one of them was triggered by an extended inquiry response, or the EIR packet. When a device scans for Bluetooth, it asks for a IER, which contains things like the device name. And the packet header has RFU, which means for reserved for future use, and these bits are that are supposed to be set to 0. But the former accidentally includes these RFU bits when calculating the total packet length. And the attacker is able to set these bits to a non-zero variable, faking like a massive packet length, which blindly overflows the hardware buffer. So now with that, we have RCE on a Bluetooth chip. So can we reach outside of it? And the answer is yes. On the Broadcom combo chips, Wi-Fi and Bluetooth run on separate ARM cores, but they share the exact same 2.4 gigahertz antenna. To coordinate the airtime, they used an enhanced coexistent interface, communicating directly with each other in the hardware without the operating system even being involved. That's crazy. And now we reach the next step, which is breaking the device. So now with all this, the researchers used this coexistent mechanism as a weapon. They used their Bluetooth RCE to escalate into the Wi-Fi components by writing these malicious data into the shared coexistent registers, and then they're able to completely shut down the Wi-Fi chip. And because the operating system wasn't expecting the Wi-Fi hardware to suddenly die, it just caused a bunch of complete kernel panics. And then the researchers were able to force devices like the iPhone 11 or some Samsung Galaxies to just like crash and reboot, which is big. And now the researchers also found a way to be able to steal data without breaking the rules. So they did that by the Broadcom chips don't have permanent storage. So the host operating system stores the link keys for paired devices. And according to the um, Bluetooth 5.2 specification, the controller chip is allowed to ask the host for a link key for a specific MAC address. And then an attacker with an on-chip RCE simply hooks that reply function and extracts the key directly from the host, completely circumventing the connection's cryptography. And they even proved they could extract keys for inactive connections, which is big. So now with all that, what if someone is attacking, let's say someone is attacking your Bluetooth chip? Can't you just toggle off the Bluetooth off in your settings? And the answer is actually no. The Bluetooth 5.2 specification states that an HCI reset command doesn't necessarily perform a full hardware reset. The researchers tested this and they found out that on iOS 12 specifically and 13 and on Android 10, turning off the Bluetooth in the setting menu doesn't hard reset the chip. The chip actually stays active, meaning turning off your Bluetooth on your screen does absolutely nothing to stop the malware running in your hardware, which is crazy when I was reading this. So now I'm gonna go into the flaw section. So as part of this presentation, we have to look at the flaws. Fixing these bugs is basically it's a nightmare. The Broadcom firmware is stored in read-only memory, people call it or ROM. And to patch a bug, I mean patch a bug, the operating system has to load fixes into a tiny RAM section called the patch RAM. But these chips only have a very limited number of patch RAM slots. And for example, there was the iPhone 6 who only has 128 slots, and Apple was already using all of them for older fixes, and this meant it was physically impossible to patch all the vulnerabilities on the older devices, which is very bad. And also about Frankenstein, it also has its own limitations. So setting up this framework is basically very labor intensive, and to support just the basic interrupts and thread switches on this specific ARM chip, that the researchers actually had to write approximately 100 custom C hooks manually. And about that link key extraction attack, there's basically no way to fully mitigate it without breaking compatibility with the current Bluetooth specification, particularly in like a simple pairing concept called the trust on first use. So there's that. And to wrap up, I wanted to say that the Frankenstein proved that emulation makes full stack fuzzing of closed source firmware not just possible, but it's very highly effective and very fast. And it shows us that wireless chips are far too interconnected. A bug in Bluetooth can take down your Wi-Fi and your whole operating system. And finally, this serves as a big warning for all of us. On modern devices, a software button that says off that you click doesn't always control the physical reality of the whole hardware. So keep that in mind. And thank you. That's all.